In our previous section, we took a look at how we could summarize data visually. But quite often, it's going to be useful to summarize data with numbers. So that's going to be our question. How do we summarize data numerically? And there's two things that we'll try and summarize numerically. The first one we're going to plant on for a minute here are the measures of center. Where is the middle of the data? And depending on our context, the measure of center will either be the mean, the median, or the mode. Let's start with the mean, or what people typically call the average. Now, if we're talking about a population mean, we will always use a Greek letter, and that's going to be the Greek letter mu. But if we're talking about a sample mean, we will use an English letter, which we will notate with x bar. And the formula for calculating the mean, I'm going to use x bar, but it works also for mu, is equal to this symbol, which we call sigma, x over n. And that symbol, that funny looking thing, means the sum. What this means is sum up all the x's, or sum up all the values, and divide by n, which is the sample size, or population size if we're in the population context. So for example, if I had the numbers 1, 3, 3, 4, 4, 4, 5, 5, and I wanted to find the mean of this sample, the numerator says sum up all the x values, or do 1 plus 3 plus 3 plus 4 plus 4 plus 4 plus 5 plus 5, and divide by the sample size. And if I count here, I see we've got a sample size of 8. So adding those all up, we get 29 over 8, which gives us a mean of 3.625, or the average is 3.625. Most students are familiar with that mean formula, but one tweak we can do to it, and we quite often have in statistics, it's not 2, let's call this C, because we're still under mean, is if we have frequencies. So we've already seen one formula for the mean, the sum of the x's divided by the n. But if we have frequencies given to us, where we know how often each number is used, the formula is going to tweak slightly. X bar is going to be equal to the sum of the x's times the frequency divided by the sample size. So if we have frequencies, we should know this formula. Let's do the exact same example we just did, but this time we're going to summarize those numbers by their frequencies. So first, I'll list out the numbers. The numbers that showed up were 1, 3, 4, and 5. But then I'm going to have another column that shows the frequency. I had a single 1. There were 2 3s, 3 4s, and 2 5s. What the sum says we need to do is first multiply the x's times the frequencies. So when we multiply, 1 times 1 is 1, 3 times 2 is 6, 4 times 3 is 12, and 5 times 2 is 10. And then what we want to do is sum this x times frequency table. So 1 plus 6 plus 12 plus 10 is 29. That represents the sum of the x's times the frequencies. And then we just have to divide by the sample size. Well, the frequencies tell us how many things there are. So my sample size is 1 plus 2 plus 3 plus 2 is equal to 8. So for my mean, again, we're doing 29 divided by 8 to get the exact same number of 3.625. But sometimes it's a lot quicker and easier if we have those frequencies given to us. That's the first measure of center. The measure of center of the average says if everybody was split up equally, they'd have this many in common. But quite often, the problem with the mean is one large value or one small value can throw off the mean significantly, which is why we might be interested more in the median or the middle number when they're first put in order. This way, one large or one small number won't have a dramatic impact on this measure of center. So for example, using our same data, the 1, 3, 3, 4, 4, 4, 5, 5, the median is going to be the value right in the middle. Well, if there's 8 values, the middle puts you between the 4 and the 4. And we know from our previous section when we made box plots, we would add those and divide by 2 to get our median value, which turns out here to be 4. And the big advantage of the median is that one extreme value does not impact the median as significantly as the mean. It's a little more stable. Now, the third measure of center, and this is often used in categories or nominal data, is what is called the mode. The mode is the value that occurs the most often. And again, it's usually best for categories. If we're talking about the color of cars in the parking lot, we're not going to have an average of a blue point green car. That doesn't make any sense. But what we can do is say the most common frequent color car is blue or gray or whatever that most frequent one is. We can still look at mode in terms of numbers. We seem to be using this example data of 1, 3, 3, 4, 4, 4, 5. So let's keep using it. And what we see is the number 4 appears 3 times. It is the one that occurs the most often. So we will say that the mode is equal to 4. Those are our measures of center, the mean, median, and mode. But the problem with just measuring the center is it only tells us where the middle value is. It doesn't tell us kind of how all the rest of the data is behaving around the center. Is the data really spread out? Is it clustered close to the center? What's happening with the rest of the data? And that's why we also need some type of measure of spread. It tells us more than just the middle. It tells us how spread out the other values are. Not just where the middle is, but how's everybody else behaving around the middle. And the reason this is important is we can look at data such as these 3 data sets I'm going to put up here. And all of them, all of the following, have the same mean and median. The first data set's going to be 1, 1, 1, 5, 9, 9, 9. Both of that data set has a mean of 5. It also has a median of 5. But if I do another data set of 1, 2, 4, 5, 6, 8, 9, that data set has a mean of 5 and a median of 5. And if I do a data set of 5, 5, 5, 5, 5, 5, 5, that data set has a mean of 5 and a median of 5. There's no difference between these three data sets if I just look at the center. But the numbers are spread out quite differently. The first data set, the blue one, are spread out very far. The green one's kind of spread out evenly. And the red one has absolutely no spread in it at all. This is why we need a measure of spread. And the most basic measure of spread is what we call the range. The range tells us how much space there is between the largest and the smallest number. We take the large number and subtract the small number to see how far apart those extreme values are. So for example, with our data we've been playing with today of 1, 3, 3, 4, 4, 4, 5, 5, the range would be the big minus the small. 5 minus 1 equals 4. And so there is a space of 4 between all of these values. Now there's a problem with the range, though. The problem with the range is one extreme value could greatly impact. For example, if there was also a 27 on this data set, 27 minus 1 would sound like 26. There's a large range between the numbers, when most of them are actually clustered quite closely together. So this is why we need a different, better measure of center. And one measure of center that might be better is what we call the interquartile range. It's often abbreviated as IQR for interquartile range. And the interquartile range you could think about as the range of the middle 50%. What we'll do is we'll take the Q3 and subtract the Q1 value. Subtract the quartiles, and we see the range of the middle 50%, or how spread out the middle 50% is. And then we're no longer going to be impacted by an extreme outlier that's way too big or way too small for the rest of the data. So for example, with our data of 1, 3, 3, 4, 4, 4, 5, 5, we already said the median was between 4 and 4. The first quartile, then, Q1, is between 3 and 3, which is just 3. And the third quartile, Q3, is between 4 and 5, which is 4.5. This means our interquartile range is 4.5 minus 3, or 1.5. And that might be a little bit of a better measure of the spread, because it's only looking at the middle 50%. The extreme outliers are not going to impact the interquartile range. However, we still have a problem. And that problem is this interquartile range formula only considers two values, the Q1 and the Q3. It would be nice if we had some measure of spread that considered all the values and how spread out those are. And this gives rise to the most important measure of spread, the one we'll use a lot in this class, called the standard deviation. And the standard deviation attempts to measure what we call the average distance a point is from the mean? How spread out is the data considering all the data values? On average, how far are they from the mean? Now, with a population, we will use a Greek letter for the standard deviation, and that's the Greek letter sigma. And with a sample, we will use the English letter S to represent the sample. The formula for the standard deviation kind of builds on this idea that we want the average distance from the mean. So if I took any point and subtracted the mean, that would give me the distance it is from the mean. The problem is some of these will be positive and some of these will be negative. So if I add them up, it actually adds up to 0. So to avoid the positive-negative problem, what we'll do is we'll square each of the values before we take the sum and add them all up. Then we'll divide by the sample size, which turns out with standard deviation, and when we derive the formula, it's not exactly the sample size we divide by, but we'll divide by n minus 1. And the reasons for the -1 are beyond the scope of this course. So you'll just have to trust me to take an average distance from the mean with the standard deviation. We're going to divide by n minus 1. The problem that we still have, though, is we squared everything, so it's not really a true average. So to undo the square, we'll take the square root at the end of our formula. And we will say s is equal to that square root. And that is going to be an important formula for us in this course. Now, I do have one little caveat. Turns out that the formula for a population standard deviation is slightly different than S. The formula is. We're not going to worry too much about that different formula for the population because generally we always have a sample. We're always going to be taking sample standard deviations, which is this formula we've looked at here. So let's do an example. And let's start with a smaller example, and then we'll move to the bigger example that we've been seeing throughout this video. We'll start with the example 11, 13, 14, and 14. And I'll give you a hint. If you go through and calculate the mean of these values, the mean is going to be equal to 13. So what we'll do to get started is we'll list our values, 11, 13, 14, 14. And then we're going to have a column for every step along the way in this formula. The first step says take those x values and subtract the mean. Subtract 13. So 11 minus 13, I can even put a little 13 here. We're subtracting 13. 11 minus 13 is negative 2. 13 minus 13 is 0. 14 minus 13 is 1. And 14 minus 13 is 1. Then the formula says to square our values. So the x minus x bar, each of those values needs to be squared. Negative 2 squared is 4. 0 squared is 1. 1 squared is 1. And 1 squared is 1. Finally, the formula says to take the sum. So the sum of x minus x bar squared is equal to 4 plus 1, which is 6. Now I'll jump to the standard deviation formula, which says the square root of the sum, which is 6, divided by 1 less than the sample size, which is 3. 6 divided by 3 is 2, and the square root is 1.41. Now, similar to our formula with means, if the data is given to us with frequencies rather than individual data numbers, we need to do a slight adjustment to our formula. So if we have frequencies, the formula will slightly adjust to s equals the square root of the sum of x minus x bar squared. But before we take the sum, we have to multiply by the frequency and then divide by n minus 1. So let's take a look at an example where we do it with frequencies. And let's use that data set that we've been using, where we know the x values were 1, 3, 4, and 5. And the frequencies of that were 1, 2, the number 4 appeared 3 times, and the number 5 appeared twice. Now, we already know that x bar, the mean, is 3.625. We would have had to find that first if we didn't know that. But since we do, now we'll make another column for x minus x bar. Taking the x, the number 1 minus 3.625 is negative 2.625. 3 minus 3.625 is negative 0.625. 4 minus 3.625 is 0.375. And 5 minus 3.625 is 1.375. Next, the formula says we need to square that x minus x bar. We're going to square each of these numbers. So 2.625 squared, and I'm going to round to 2 decimal places, is 6.89. 0.625 squared is 0.39. 0.375 squared is 0.14. And 1.375 squared is 1.89. Now, if we didn't have frequencies, we would just add this column up. But because we have frequencies, we need to take this column, the x minus x bar squared, and multiply by those frequencies. So the 6.89 needs to be multiplied by 1 to get 6.89. The 0.39 needs to be multiplied by its frequency of 2 to get 0.78. 0.14 times 3 is 0.42. And 1.89 times 2 is 3.78. And that's what we want to sum. We want to get the sum of x minus x bar squared times the frequency. And when we add up that column, you should end up with 11.87. Now we plug into our formula for s. S is the square root of that sum we just found is 11.87. Divided by 1 less than the sample size. You could add the frequencies together to find out that the sample size is 8. Or you might remember that, because we've been working with this for quite a while. 1 less than the sample size is 7. So the square root of 11.87 divided by 7 is 1.30. So on average, these points are about 1.30 units away from the mean of 3.625. It gives us an idea of the middle and how spread out the data actually is. Now, the standard deviation is actually quite nice because it gives us a way to compare data based on how many standard deviations we are from the mean. Standard deviations measure distance from the mean. And in statistics, we will use a very important variable to represent the number of standard deviations we are from the mean. That variable is always going to be z. Z is the number of standard deviations from the mean. And we actually have two formulas that use z. They're both really the same formula. The idea is z is the number of standard deviations from the mean. So we'll take the value we're working with. We want to know how many standard deviations x is from the mean. Well, first we need to know the distance to the mean. So we'll subtract the mean, or x bar, and then we'll divide by s, or the number of standard deviations that is. That's our main formula for z. Now, sometimes we have the opposite information, and we want to know what is 3 standard deviations from the mean. We know z. We want to be 3 standard deviations from the mean. What value is that? And so we can solve this equation for x. And when we do, we get x is equal to the mean plus the number of standard deviations times the standard deviation. And so this formula, it's really the same formula. It's just been solved for x. Will tell us the number of standard deviations is what value. Let's do some examples. Let's say for our data, 1, 3, 3, 4, 4, 4, 5, 5. We want to know how many standard deviations from the mean is the median. Well, we've already found all these important values. We found the median is equal to 4. Also, earlier, we found the mean was equal to 3.625. And also, earlier, we found the standard deviation is equal to 1.3. So if we want to find out how many standard deviations the median is from the mean, the medians are x, the mean's the x bar, and the standard deviation is s. So z, the number of standard deviations, 4 is, we subtract the mean of 3.625 and divide by the standard deviation of 1.3, and we find the median is 0.288 standard deviations from the mean. Or we could ask a similar question for the same data. What value is 2 standard deviations below the mean? We already know the number of standard deviations. So 2, that's actually going to be our z, the number of standard deviations below the mean. And because we want to be below the mean, we will use a negative number to make it below the mean. So we're looking for the x this time. What is that value of interest? So x is equal to the mean, x bar of 3.625. Minus 2, because we have a negative 2 standard deviations below the mean, times the standard deviation of 1.3. And that gives us 1.025. Now, it turns out that we can say 95% of our data generally falls within 2 standard deviations of the mean. If it's more than 2 standard deviations from the mean, we say those values are unusual or extreme values. We call those extreme values outliers. And these outliers are values far removed from the rest of the data. For example, if I have the numbers 1, 3, 3, 5, 87, 87 is far removed from the rest of those values. It's an outlier. And the outlier can either be large or small. And we actually have 2 methods for calculating outliers, and they generate very similar results. So neither one is necessarily better than the other, but I want to show you both of them. The first one is called the interquartile range method. And the idea behind this is we cannot be more than 150% or 1.5 times the IQR from the edge of the box in the box and whisker plot. The idea is anything below the first quartile minus 1.5 times the IQR, or anything above the third quartile plus 1.5 times the IQR. Anything that's above or below those numbers becomes an outlier. So for example, let's say we've got the numbers 2, 3, 5, 6, 7, and 14. Now, the median's right in the middle. But what we're interested in with the interquartile range is the middle below the median. The first quartile is 3. And the third quartile is 7. So the interquartile range is 7 minus 3, or 4. This means an outlier is anything below the first quartile, 3, minus 1.5 times the interquartile range of 4. That gives us 3 minus 6, or negative 3. Anything below negative 3 would be an outlier, which there's nothing in this data set below negative 3. But also anything above the third quartile, 7, plus 1.5 times the interquartile range. 7 plus 6 is 13. Anything above 13 becomes an outlier. And you notice 14 is right on the edge there. And so we will say, based on that, 14 is an outlier. It lies outside of the majority of our data. Now that's the interquartile range method. I said there's a second method. It's based on the standard deviation. The standard deviation method says that anything that is more than 2 standard deviations from the mean is an outlier. Which brings us back to that example that led into this discussion. So actually, let's first define this clearly. Let's do anything below x bar the mean minus 2 standard deviations, or anything above x bar the mean plus 2 standard deviations is considered an outlier. So for example, we had our data of 1, 3, 3, 4, 4, 4, 5, 5. And we found out already that the mean of this data is 3.625. And we also found out the standard deviation of this data is 1.3. So an outlier would be anything below the mean, 3.625, minus 2 standard deviations. (3.625 minus 2 times 1.3 is 1.025. And we'll recognize there that we do have a value below 1.125, or 1.025. It's just a little below, but it is below. Here, 1 is an outlier. We also have to check above. So we'll do the 3.625 plus 2 standard deviations, or 2 times 1.3, which gives us 6.225. Nothing above 6.225, so the only outlier we have here is the number 1. So we've covered quite a bit in this video. We talked about measures of center, the mean, median, and mode to estimate where the middle of the data is. We talked about measures of spread to see how spread out we are around the mean or the center, using the range, the interquartile range, and the most important ones, the standard deviation. And then we also looked at some uses of the standard deviation to see its distance from the mean, finding outliers or identifying outliers. So lots to take a look at on the assignment. Take a look and practice a few. We will discuss them more in class. We'll look forward to seeing you then.